Hello friends, continuing with the topic of transistor. Today we come to next part of it, three configuration of a transistor. What is the topic for today? Today's topic is three configurations of a transistor. Now you know an electrical circuit has four terminals. Two input terminals, two output terminals. But transistor has only three terminals. Therefore, one of the terminals must be taken as common between input and output. And accordingly, a transistor has three configurations. First, common base configurations, in short CBC, where base is common between input and output. Second, common emitter configuration, in short CEC, where emitter is common between input and output. 3. Common collector configuration, CCC, where collector is common between input and output. Now we are to draw three configurations of transistor using PNP transistor as well as NPN transistor. So let us draw three configurations using PNP transistor. So this is common base configuration, this is common emitter configuration, this is common collector configuration. In common base configuration, base is common between input and output. In common emitter configuration, emitter is common between input and output. In common collector configuration, collector is common between input and output. Now, three configurations of a transistor using NPN transistor. So this is common base configuration where base is common between input and output. This is common emitter configuration where emitter is common between input and output. This is common collector configuration where collector is common between input and output. So thus these are three configurations of transistor. Second, by seeing three configurations of the transistor, there are two types of transistors, PNP transistors and NPN transistors. First, we take up PNP transistor. How we apply bias using PNP transistor? The simple trick is connect battery through a resistance to the respective terminals as shown in diagram. How we name the resistance and battery? The method is take the first letter of the terminal and in small size put in the leg of resistance and in capital size put in the leg of the battery 2 times. Okay. So this is the method how we apply bias to any configuration of the transistor of any type. Now first we take up common base configuration. Now VEE is forward bias applied to emitter through RE, and VCC is reverse bias applied to collector through RC. Now this is common emitter configuration in which VBB is the forward bias applied to base through RB and VCC is the reverse bias applied to collector through RC. Now this is common collector configuration. Here VBB is the reverse bias applied to the base terminal through resistance RB, and VEE is applied to the emitter terminal through resistance Re. Now, since VBB and VEE, if taken together, are connected in series but in opposite polarity, so therefore the two cells will neutralize and only one cell will remain in emitter region, which will form the forward bias between emitter and base. Okay. Now let us apply bias using NPN transistor. Now this is common base configuration. VEE is the forward bias applied to resistance Re, and VCC is the reverse bias applied through resistance Rc. Now this is common emitter configuration, where VBB is the forward bias applied through resistance Rb between base and emitter, and VCC is the reverse bias applied through resistance Rc between base and collector. Now this is common collector configuration of the transistor, where VBB is the reverse bias applied through resistance Rb between base and collector, and VEE is the forward bias applied through resistance Re between base and emitter. Since the two batteries VBB and VEE are in series, and the two cells will cancel, and the remaining one cell in emitter region will constitute the forward bias between base and emitter. And this is how we apply bias to the three configuration. You remember the simple trick: take the battery and connect through a resistance to the respective terminal according to the requirement of the bias. Okay. Now, uses and comparative study of the three configurations. Now, here we have shown 4 columns. In the first column, we will write the characteristic of common base configuration, common emitter configuration, as well as common collector configuration. So, comparatively, we will study the how characteristics vary between the three. Now, first characteristic, we talk of use, how the three configurations are used. Common base configuration is used as voltage amplifier. Common emitter configuration is used as voltage as well as power amplifier. Common collector configuration is used as emitter follower. Now, second, phase relationship between input and output signals. In common base, now second, phase relationship between input and output signals. In common base configuration, input and output signals are in phase. In common emitter configuration, input and output signals are out of phase. And in common collector configuration, the input and output signals again are in phase. Now third, voltage gain. Voltage gain AV is equal to V output over V input. In case of common base configuration, voltage gain AV is of the order of hundreds and thousands. In common emitter configuration, voltage gain AV is of the order of hundreds. And in common collector configuration, voltage gain AV is less than 1. Now fourth, current gain of current. Now fourth, current gain or current amplification factor AI, which is equal to I output over I input. Now fourth, current gain or current amplification factor. It is denoted by AI, which is equal to I output over I input. For common base configuration, it is denoted by alpha, which is equal to IC by IE and is less than 1, is of the order of 0.9. For common emitter configuration, it is denoted by the symbol beta, which is equal to IC by IB and is more than 1, is of the order of hundreds and thousands. Now for common collector configuration, it is again denoted by beta, which is equal to IC by IB and is more than 1 and is of the order of hundreds and thousands. Fifth, power gain. Power gain is equal to AV into AI. Now for common base configuration, power gain is low. For common emitter configuration, power gain is high. For common collector configuration, again power gain is high. Now sixth, input and output impedances. For common base configuration, input impedance Zin is 20 kilo ohm, output impedance Zo is 100 kilo ohm. Now sixth, input and output impedances. For common base configuration, input impedance Zin is 20 kilo ohm and output impedance Zo is 100 kilo ohm. For common emitter configuration, Z input is 100 kilo ohm and Z output is 120 kilo ohm to 1 mega ohm. And for common collector configuration, input impedance Zin is 120 kilo ohm to 1 mega ohm and Z output is 100 ohm to 600 ohm. Okay, input impedance is very high, output impedance is low. It is used as matching device or buffer amplifiers, etc. Now assignment 14 continued. Question number 52. Why common emitter configuration is preferred over common base configuration? Now after studying about 3 configurations of a transistor, we come to fourth part of it, alpha and beta of a transistor. First we take up alpha of a transistor. Alpha of a transistor or current gain or current amplification factor. These are 3 different names for alpha of a transistor. Either we say alpha, or we say current gain, or we say current amplification factor. Now let us take up definition of alpha. In 2 ways we define alpha of a transistor, alpha DC and alpha AC. So let us try to understand how we define alpha DC. The ratio of collector current to emitter current of common base configuration of the transistor under static conditions, that is when it is only biased, is defined as current amplification factor or alpha DC, mathematically expressed as alpha DC as equal to IC by IE. Now look at this circuit diagram. This is the circuit diagram of common base configuration when applied with bias. Now this is IE emitter current, this is IC collector current, and this is base current. The ratio of collector current to emitter current, that is output current to input current, is defined as alpha DC. Okay. Now let us take up definition of alpha AC. It is defined as the ratio of change in collector current to change in emitter current of common base configuration of the transistor under dynamic conditions, that is when applied with AC signal at the input. Mathematically expressed as alpha AC is equal to delta IC by delta E, or it is equal to small IC by small IE. Because when you write the symbols for changing current, we use small letters. When we write the symbol for direct current, we use the capital letters. So here we have used the change in collector current, which is denoted by small letters. Now look at this circuit diagram. When we apply AC at the input, the emitter current changes to capital IE plus small IE. Accordingly, collector current also change from capital IC to capital IC plus small IC. So the change in collector current is small IC and change in emitter current is small IE. Therefore, alpha AC is equal to small IC by small IE. This is how we express alpha AC. Now alpha DC is only when we bias the transistor, and alpha AC is when we apply signal at the input, that it comes under dynamic conditions. Okay. Now let us take up beta of a transistor. Its other name is current gain or a current amplification factor. Now definition of beta DC. The ratio of collector current to base current of common emitter configuration of the transistor under static condition, that is when applied with only bias, is defined as current amplification factor or beta DC, mathematically expressed as beta DC is equal to IC by IB. Okay. Now look at this circuit diagram. This is circuit diagram under static conditions. This is the base current input and the collector current at the output. So ratio of collector current to base current is IC by IB. So beta DC is equal to IC by IB. Now let us define beta AC of the transistor. The ratio of change in collector current to change in base current of common emitter configuration of the transistor under dynamic conditions is defined as beta AC of the transistor, mathematically expressed as beta AC is equal to delta IC by delta IB, or it is equal to small IC by small IB. The same way we defined as we have defined alpha. Now look at this circuit diagram. At the input we apply AC, and that at the output also we get AC, which is out of phase. Now input current is capital IB plus small IB, because IB changes according to the input signal. Now output current is capital IC plus small IC. So change in collector current is small IC, change in base current is small IB. Therefore beta AC is equal to small IC by small IB. Now relationship between alpha and beta of a transistor. whether it is DC, whether it is AC. The relation is same. Now, since we know in a transistor IE is equal to IB plus IC, let us mark it as equation 1. And alpha is equal to IC by IE, let us mark it as equation 2. And beta is equal to IC by IB, let us mark it as equation 3. Therefore, substituting the values of IE from equation 1 in equation 2, we get alpha is equal to IC divided by IB plus IC, or it is equal to 1 divided by IB by IC plus IC by IE, or it is equal to 1 divided by 1 by beta plus 1, because IB by IC is equal to 1 by beta and IC cancels. So we have alpha is equal to 1 divided by 1 by beta plus 1. On simplification we get it is equal to beta divided by 1 plus beta, which is less than 1, because denominator is more than 1 and numerator is equal to beta. So therefore it comes out to be less than 1. Now alpha is equal to beta over 1 plus beta. On simplifying this equation we get alpha equal to beta over 1 plus beta. Let us mark it as equation 4, and is always less than 1, is of the order of 0.9. Now circuit diagram is same. This is for DC conditions and this is for AC conditions. Okay, so whether it is beta DC or beta AC, accordingly you choose the circuit. If beta AC is asked, to choose the circuit for AC, and if beta DC is asked, you choose the circuit for beta DC. Using simple algebraic operations, we can find the value of beta from equation 4. Cross multiplying equation 4, we get beta is equal to alpha into 1 plus beta, and it is equal to alpha plus alpha beta. From here we find beta minus alpha beta is equal to alpha, or beta into 1 minus alpha is equal to alpha. Here we take out beta common, or beta is equal to alpha over 1 minus alpha. Let us mark it as equation 5, and is always more than 1, because denominator is less than numerator, 1 subtracted by alpha, and is of the order of hundreds and thousands. Okay, so remember the expressions: alpha is equal to IC by IE, beta is equal to IC by IB, and also alpha is equal to beta over 1 plus beta, and beta is equal to alpha over 1 minus alpha. You remember these expressions for solving numerical problems. Assignment 14 continued. Question number 53. For a transistor working in a common base configuration, the current gain is 0.96. If the emitter current is 7.2 milliampere, calculate base current of the transistor. Question number 54. The base current of a transistor is 105 microampere and collector current is 2.05 milliampere. Determine the value of beta, IE and alpha of the transistor. Thank you so much. Next time we'll take up next part of it. Till then, goodbye and good luck to you.